Hello, Algebra 1 students. It's Mr. Ford here with a homework tutorial, and today we are talking about 532 Part 1 homework. That's 101 through 106. There is not a checkpoint question incoming. I got to fix this on these ones. Jeez. All right, so 5101, we're probably going to want a calculator for, because if you're thinking about this, well, the first one you don't. We are really used to seeing things in a linear pattern, meaning you're adding the same number every time. But that's not the case here. For this table, we're going to find the missing entries and we're going to write the equation. For the first table, though, if you look at this, if you try adding 6 to get from 2 to 8, that pattern does not work for the next entry in the sequence. 8 plus 6 is not 32. So we need to think of a different way. And really, the new thinking with these kind of tables is we're going to multiply by 4. We're multiplying by 4 each time. Now, filling out these tables is going to be kind of arduous because the numbers are going to get real big real fast. And so let me grab my calculator and pull it up to the front screen. So we're going to figure this thing out. Let's try 32 times 4, which is 128, and then you get 512, and then you get 2048, and then you get 8192. The numbers get real big real fast. 128, 512, 2048. Oh, tablet creeped out of me. 2048, and 8192. Things get real big real quick here with this table. Now, as far as the pattern goes, though, the equation is going to be really easy to write if you've been paying attention. The next term in the sequence will be the original 0 term, which was 2 in this case, times the constant multiplier of 4, all to the nth power. So what we're doing is taking 2 and multiplying it by 4 some number of times. The same pattern holds with the second table, although it's not as obvious what the multiplier is. I mean, the same thing happens, though. You can't do plus 1 because 6 plus 1 is not 7.2, so it's not that. In general, a good strategy for these problems, if you think it's being multiplied by a constant number, just take any one of the numbers. Like, let's try 6 divided by 5, and you get 1.2. If you take that same division problem, try 7.2 divided by 6. Divide any number by the previous number, and you get the same thing. And this tells you that we're multiplying by a pretty constant 1.2. So if you take 7.2 and multiply by 1.2, you'll get 8.64. And then you get 10.368. And you get the next few numbers. I mean, these are all decimals, so do your best to round them as best you can. 8.64, 10.368. The numbers don't matter so much as the pattern. 12.4416. Oops, tablet. Crap them out on me again. And then 14.92992. If you want to be real fancy about it, sure, fill those numbers in. For the rest of this, though, we're going to need a formula. And for the formula, we're going to need the same parts. Start with the 0th term, which is 5. You're going to have t of n equals 5. And we're multiplying this time by 1.2 to the nth power, just like that. So math respects you when you respect it back. Look at the patterns going on. Whatever the 0th term, that's that number. And whatever the multiplier is, that's that number. Otherwise, it's got the exact same bones to it every time. So make sure, if you're following along with this video, make sure you are thinking about what we're doing and not just copying down what I'm writing. Think about what's going on. We did 102 in class for the most part, so I'm not going to talk about it too much here. This is how we find the multiplier based on a percentage increase or decrease. 103, Mr. C is such a mean teacher. The next time Matthias gets into trouble, Mr. C has designed a special detention for him. Matthias will have to go out in the hall and stand exactly 100 meters away from the exit door and pause for a minute. Then he's allowed to walk exactly halfway to the door and pause for another minute. So here he is at M, and there's 100 meters away. So he goes halfway to 50, and then he goes halfway again to 75. And then that pattern goes on and on and on. And when Matthias reaches the door, he can leave, unless he breaks the rules and goes more than halfway, even a tiny amount, and prove that when he can leave. We have talked about this a few before. This is thing, if you want to go on Google right now, you can look this up. This is called Zeno's paradox. And the idea is that you can't ever get to any location, because before you get there, you have to go halfway. Half of 75 is right there, and then half of that will be right there, and then half of that will be somewhere right here, and then half, and then half, and then half, and then half. And the idea is that you can never actually get to 100 because you have to just keep going half of the distance. And as long as you zoom in a little bit on the number line, let's say this is now 100, and this is like, I don't know, 99.999, there are still going to be a half, and then a half, and then a half, and then a half, and then a half. And you can zoom in again, one more layer. There's always going to be another little half you can go. Of course, if you add up all these little tiny halves over time to infinity, you eventually get the entire number, which is why you can go all the way to the door. But this is the thinking here. This is why when you raise, and this is why a times b to the x power will never equal 0. But we'll talk about this a lot in class. You can never get to 0 by multiplying over and over again. You can't get there. Let's talk about some exponent rules. We actually had a checkpoint quiz over this already, but we're going back in time to review it because it's important to keep it in the forefront of your brain. Let's let my tablet figure out what it wants to be right now. For this first question, let's deal with the numbers first. 2 times 4. 2 times 4 gives you 8. And m to the third times m squared gives you m to the 5th power. We're going to combine those together. For question B, 6 divided by 3 is going to give us 2. And then y to the 5th divided by y to the 2nd power, that's going to give us 5 minus 2, which is y to the 3rd power. 2y to the 3rd. Question C, negative 4 divided by negative 6. That's not going to be an even number, but they're both even. So you can at least reduce that fraction down. This is going to be negative 2 on top and 3 on bottom, leaving some space for the other stuff too. Now, this is interesting. These two y's are going to cancel out 2 of these y's, leaving y to the 5th on the bottom, like that. So that is my final answer. I'll clean it up a little bit. Negative 2 over 3y to the 5th, like that. Yeah, I suppose you could write this as negative 2/3 times y to the negative 5th if you want to. That's the same idea. Question D, same kind of thing. This time we're raising it all to the 3rd power. So negative 2 to the 3rd power is negative 2 times negative 2 times negative 2, which is negative 8. So this is going to be negative 8x to the 6th power. 2 times 3 this time. So we have x squared times x squared times x squared, and that's 6 x's altogether. There you go. Next page. 5105, refer to the sequences graphed below. Identify each sequence as arithmetic, geometric, or neither. Okay, so arithmetic adds the same number every time and makes a linear graph. Geometric multiplies the same thing every time, and so makes a curvy graph. So we can at least take a look at a few of these things. I would say number 1 is definitely arithmetic, because it is going down by, it looks like 3 every time. Down by 3, down by 3, down by 3. It's a nice linear graph. I think that's the key. This nice straight line is developing, and that's linear, which means it's arithmetic. Now, between question 2 and question 3, it's interesting. They both make curvy graphs, but one of them is exponential and one of them is not. The one that is geometric is number 3. This is geometric. And here's the thing about geometric sequences. Geometric sequences only increase or decrease. Here's the dead giveaway. They never do both, because when you're multiplying by a number, you can either keep getting bigger or you can keep getting smaller, but you can't just turn around and suddenly start going bigger again. That's not going to happen if you're multiplying by the same number every time. So that's how I know that number 3 is geometric. Number 2 is actually quadratic, which we will deal with at the very end of this class, which we also say is neither. Number 2 is going to be your quadratic equation. It's neither arithmetic nor geometric, because it turns around is the dead giveaway. It's got a parabola going on. Now, so for question B, if it's arithmetic or geometric, let's describe the sequence generator. So let's talk about number 1. So the sequence generator just means what's the equation, what's going on every time to get to the next term. It looks like we're going to the right 1 and down 3. Right 1, down 3, right 1, down 3. So I would say that the sequence is subtracting 3 every time. And all we have to do, if we're describing the sequence generator, that's all we really need to do is talk about what's happening every time. What are we multiplying by or adding? I guess you could say adding negative 3 if you wanted to. For number 3, we appear to be starting at the number 16, and then the next number is the number 8. I'm just looking at the y-axis for that. The next number is 4, and then 2, and then 1, and then 1/2. So I think what's going on here is we're multiplying by 1/2. Or if you want to, you can say dividing by 2. But as we talked about before, multiplication and division are actually the exact same thing. You can turn any multiplication problem into a division problem and vice versa. So let's talk about the last question here. We did a little bit in class about this. When you see a sub n, that is just another way to write t of n. And if you see a sub 1, this means the first term. A sub 2 means the second term. A sub n is the nth term, and so on. So this is just a different way of writing the answer. So I guess I'll erase. The answer's already here, but I'll erase and work through it again. So for the first 5 terms of the sequence, which was what we need to do, all you got to do over here, question A gives you an explicit formula. So if you want to know what the nth term is, you just plug in the number. So we plugged in 1 and 2 and 3 to figure out the first 3 terms. 2 times 1 minus 5 is -3. 2 times 2 minus 5 is -1. 2 times 3 is 6, and 6 minus 5 is +1. And then you might see the pattern happening. We're just going up by 2 each time, which should make sense because the equation is 2n minus 5. So we're starting at -5 and going up by 2 every time. The next number would be 3. The next number after that would be 5. And so those are the first 5 terms right there. For question B, you've got a recursive pattern. And for that, they've told us what the first number is. That's 3. So the first number in our sequence is the number 3. So we're going to go ahead and start with 3. Oh, boy. There's a significant delay today on when I select a pen and when I can actually write in that pen color. No, it's a highlighter still. No. Rats. Hang on a minute. Stand by. I want to reboot this program here. Close you. You see Slope Dude there. Open up OneNote. Here we go. And we should be back. Kind of. I know, that last problem I should have practiced. Oh, no. Okay, here we go. We're back. Oh, look, the answers are back, too. Cool. I thought I erased them. That's all right. The first number is 3. But then the pattern tells you that what you're going to do for the next number is you're going to multiply it by -2. So all we're going to do here is we're just going to take the number -3 and multiply it by -2. Come on. Killing me. Absolutely killing me here. I am selecting a pen. I want to write in a pen. There we go. So we're going to multiply by -2 and get -6. The next number, multiplying by -2, would be +12. The next number after that is -24, and then +48. You're just doubling the number, and you're alternating whether it's positive or negative because you're multiplying by a negative. So we got positive, negative, positive, negative, positive. And the next number will be -96, like that. I hope you enjoyed this video. Hope you got the homework done. You guys are great and awesome, and you're going to keep going through the end of the year, and I am excited to be a part of it. So I'll see you in the next video.